Okay, welcome to lecture here. We'll get started here in just a second or continue where we left off. Chapter 18, I think. All right. Excuse me. We are talking chapter 18. We started talking about redox reactions. And again, we really sort of went over here talking about balancing redox reactions, oxidation states, just to make sure, again, that everybody's sort of on the same page with that. Again, might depend on who you had or where you took the first semester as to maybe how much of the sort of redox balancing and working those equations out that you have done in the past. So again, I just want to make sure everybody's sort of on the same page with this. So remember, redox reactions are oxidation reduction reactions. The basic definitions that we use, usually in general chemistry, is the idea of electrons either gaining or losing electrons. So when we lose electrons, something goes through oxidation, becomes basically more positive. And when something gains electrons, it goes through reduction and becomes more negative in that case. And again, the oxidizing agent is the substance that gets reduced. So remember that the oxidizing agent is the thing that's actually getting reduced, and that is because it causes the oxidation in the other species. So in order for it to be reduced, it has to gain electrons. And in order for it to gain electrons, it's got to cause somebody to lose electrons and go through oxidation. That's why it's called the oxidizing agent. And the reducing agent, again, is sort of the opposite there. The reducing agent is the substance that goes through oxidation. In order for something to get reduced, it has to gain electrons. So it is supplying the electrons that allows something to get reduced. And so oxidizing agent, reducing agent, basically opposite of the names is a good way to remember that. So oxidizing agent, thing gets reduced, reducing agent, the guy gets oxidized. And again, you can follow the oxidation numbers basically to sort of figure out what is happening. When we write our half reactions, remember that in terms of oxidation half reactions, the electrons should be on the product side as they're being given off or lost. And for a reduction half reaction, the electrons should be on the reactant side like they're being gained. Now, as we gain and lose electrons, they always sort of happen together in terms of oxidation reduction. So however many electrons are lost through oxidation should be how many electrons are gained through reduction. So the important part when we have those half reactions, as we talked about, is that you want to make sure that they are the same number of electrons in each of the half reactions, because there should be sort of a complete transfer of electrons, basically from one to the next, or a loss of one and a sort of acceptance on the other part. When we do balance these guys in acidic and basic conditions, it's a little bit more complicated, if you will. You need to add water and so forth to balance these guys out. So we did one together. I think I asked you to do some of these next couple of examples at home so we could go over them here and sort of see how you did. So we'll do that here. We left off, I think, with this one. And so we have this reaction here. We want to balance it in basic conditions. So the first thing that you want to really do is sort of split it off into its two half reactions. So this would be I minus to I2. And the other half reaction would be the guys that kind of go together, MnO4 minus going to MnO2. We could also kind of look and see what's happening here in terms of their oxidation numbers. The iodide here is -1, so -1 for that guy. The I2 on this side is 0. So in this case, if you remember that sort of number line you could use to help you out on that, it is starting at -1, which would be over here. It is heading in that direction towards 0, which means that it is becoming more positive and is going through the oxidation. So this would be our oxidation half reaction. The I minus would be our reducing agent in that case. In terms of the MnO4 minus, The oxygen is -2, and there's 4 of them, which gives you a -8, which means the Mn in this case has an oxidation state of +7, while when we go to the other side, the oxygen is -2. There's 2 of them, which gives you 4. Here it has a +4. So in the case of the Mn, is starting at like +7 down this way, and it's heading towards +4, which is going in the left direction, and means that this is our reduction half reaction. Also means MnO4 minus there would be our oxidizing agent in this case. By the way, if you could determine just one of those things, you don't necessarily determine both of them, but if we were able to determine like we did that this was the oxidation, by default, obviously this would have to be the reduction or vice versa. Now, once we sort of have it split off, we want to balance all the other elements besides oxygen and hydrogen. So we do need to put a 2 here in front of the I minus. And in case down here, we have Mn on both sides, 1. So we don't need a balance in that particular case. Next, we want to balance the oxygens with water. In the case of the first half reaction, there is no oxygen, so we don't have to worry about it. On the bottom here, we have 4 oxygens on the left, 2 on the right. So we do want to add 2 waters to the right-hand side to balance out the oxygen. As we talked about, when we do add the water, we're also adding H's. So because we added basically 4 H's to the right-hand side, to the left-hand side to balance it so we are not short, we do need to add 4 H pluses. At this point, we've now pretty much balanced all the elements, including hydrogen, oxygen, and everybody else. The next thing that we want to do is add electrons, and we want to add electrons to make sure that the overall charge on each side is the same. Again, does not have to be 0. So in this case, on the left-hand side for the I minus, we have 2 minus, or -2. On the right-hand side, the overall charge is 0. So the top guy will need 2 electrons on the right-hand side. That gives us -2 on the right and -2 on the left. This also makes sense because this is our oxidation half reaction, and we added the electrons to the right-hand side, which is where we want them. Now, in terms of our reduction here, we do have +4 here and -1. So over on the left-hand side, we actually have +3. The overall charge on the right-hand side is 0. So we're going to need to add 3 electrons. I'll squeeze them in. 3 electrons there to the left-hand side. That's going to give us an overall charge of 0 on the left and 0 on the right. Also makes sense because this is a reduction. So our electrons are over here on our reactant side. Any questions so far? Now, really, we're at the point, and obviously if you do have questions, feel free to ask, but obviously we are at the point where we're going to add these together. And before we can add them together, we do need to make sure that we have the same number of electrons in each. So in this particular case, we have 3 electrons on the top one, or 2 electrons on the top one, and 3 on the bottom. So the common number there is going to be 6, which means we need to multiply the top equation by 3. And we need to multiply everybody in the bottom equation by 2. So I will rewrite that underneath. Let's see here. Grab a different color maybe. All right. So if I rewrite all that, try not to mess it up here, we're going to get 6I minus goes to 3I2 plus 6 electrons. Again, just distributing that 3 across. I'm going to distribute the 2 on the bottom one. So that's going to give me 6 electrons plus 8 H pluses plus 2 MnO4 minus 2 MnO2 and 4 waters. Now I can add these together. I'm going to cancel out the 6 electrons on both sides as they do cancel. Remember, anything that's on opposite sides of the arrow, that's the same. You could either cancel out completely if it does or reduce down. And then everybody on the left will stay on the left. So I'll have 8 H pluses plus 2 MnO4 minus plus 6 I minus. goes to my right-hand side, 3I2 plus 2MnO2 and 4H2O. Now, if I stopped right at this point, this should be the balanced equation in acidic conditions. So I have 8 hydrogens on the left, 8 on the right, 2 MNs on the left, 2 on the right, 8 oxygens on the left, 4 and 4 is 8 on the right, and 6 I's on each side. Overall charge on the left-hand side, I have plus 8 and minus 8, which is 0. Overall charge on the right-hand side also equals 0. So if we were asked to, again, balance this in acidic conditions, we basically would just put a box on that and we would be good to go. But we are doing basic conditions. So as I mentioned last time, probably the easiest thing to do is just to balance it in acidic conditions like we did. And now when we're in basic conditions, what we want to do is look at how many H pluses we have, which is 8 in this case. And that is how many hydroxides we should add to not one side, but both sides of the arrow. And when we do that, this part over here, which is where we have H plus and OH minus, they will combine to make water. And what I'll do, I'll just write up here since I have a little bit more room, I think. So those guys are going to combine to make 8 waters plus 2 MnO4 minus plus 6I minus gives me 3I2 plus 2 MnO2 plus 4 waters and 8 HOH minuses. At this point, usually what happens is what we see here, we will have some waters we could also cancel. So I'm going to get rid of 4 there, and this will now become 4, and that basically leaves us with the actual balance equation, which would then be 4 waters plus 2 MnO4 minus plus 6I minus goes to 3I2 plus 2 MnO2 and 8 OH minuses. And this should be the balanced equation in basic conditions. And again, if we just kind of go through it, we got 8 hydrogens on each side. We got 4 and 8, which would be 12 oxygens on each side. We also have 2 MNs on each side and 6 iodides or iodine. And overall charge on the left-hand side is now minus 8. Overall charge on the right-hand side, minus 8 as well. So again, when you balance these, should be balanced 2 ways, both element-wise, like a normal equation, and also charge-wise. Again, does not have to equal 0 on both sides, but does need to have the exact same charge on each side. Any questions on any of those steps there along the way? Okay, so all right, we'll do one more here just to make sure. So we'll run through this one here. Again, we're doing basic conditions, so we want to split it off. So that's going to give me that and this guy. That will also give me this and that. And when we look about what's happening here, this is going to be plus 2. The Mn over here, this oxygen is going to be minus 2. It's going to be plus 4, which means our Mn here is going from plus 4. I'm sorry, plus 2. I'll learn to count. Plus 2 going to plus 4, which means it is going to the right-hand side and going through oxidation. Now here you may be wondering what's going on here. What's going on here is actually the oxygen is minus 1 in this case, since this is hydrogen peroxide, and this is plus 1. Over here it's minus 2 and plus 1. It's actually the oxygen here that's changing. The oxygen started at minus 1, and ended up at -2, which is going in that direction and going through reduction. So here it's actually the oxygen going through the reduction part. We're still going to kind of follow the same approach here. Mn is the only other element there. We have one on each side, so we don't have to worry about it. In this case, we do need to add 2 waters for the 2 oxygens that we have here. When we do that, we also need to add our 4 H pluses. Now, when we come to the bottom one, we actually have 1 water that needs to be added. So you could do it either way. I'll just do it separate if you want, so you can see the water being added. You could just put a 2 in front of here if you like. When you do that, again, the key here is we want to add 2 H pluses, right? Again, because we only technically added 1 water, so we don't want to go crazy with the H pluses. At this point, we then want to balance out the charge with our electrons. Overall charge on the left is +2. On the top here, overall charge is +4, which means I think we need a couple of electrons on that top one. On the bottom, overall charge on the left is +2. Overall charge on the right is 0, which also means a couple of electrons here as well. If I didn't mess that up. That actually means we do have 2 electrons on each side, which means that they will cancel. And if we do that, believe it or not, our waters here will also do a little bit of canceling. And I think that's all my canceling at this point. We will end up with Mn2 plus a little H2O2. Gives me some MnO2 plus some 4H plus. This technically, excuse me, this, I think I missed 2 H's over here, huh? That would be not good. There. And so this actually would become 2 H pluses on that side. I missed that guy sitting right there. So this guy and this guy would cancel down to get us to 2 H pluses. And now if we look at it, we are balanced. We have 2 H's on each side, 2 oxygens on each side, and an Mn on each side. So this would technically be our equation that is balanced for acidic conditions. And at this point, since we're doing basic, we would add 2 OH minuses again here to both sides. This is going to combine to make water. So this will leave us 2 OH minus plus Mn2 plus H2O2 gives us MnO2 and a little H2O action going on there. And we should now be balanced in basic conditions. That's 2 oxygens and 2 is 4. So 4 oxygens, 2 Mns, and 2 hydrogens is 4. Overall charge on the left-hand side looks like a 0. Overall charge on the right-hand side, also 0 in this case. And we are balanced. Any questions on how to balance these redox reactions or equations? Okay, so did have one more. Maybe we'll skip it, I think. Yeah, everybody good on that, I think. Hopefully. All right, so again, that was sort of a review-ish type of situation there, just to make sure everybody's on the same page in terms of that. So now what we're going to talk about really is galvanic cells, and galvanic cells are really redox reactions that occur. So galvanic cells are essentially oxidation reduction reactions that occur. This is your classic sort of galvanic cell that you would set up in a laboratory. A lot of times you'll have 2 beakers such as this. And inside the beakers, you'll have some solutions. You typically will have some solid electrodes attached into the solution. And typically the solution contains the ion form of the solid electrode. So for example, this is zinc in the solid form here. Floating around in the solution are the aqueous ions of zinc in that particular solution. On the other side over here, we see our solid electrode is copper, and floating around in that solution is basically the copper 2 ions. There's some negative ions in there as well, again, because it's most likely an ionic compound. They are connected via a wire. You could have a voltage meter, which will give you the voltage of this particular cell. And basically the electrons are traveling down to the other side. On this side over here, where it is labeled the anode compartment is where oxidation occurs. So this is where we lose electrons, which is why we see the electrons traveling down in this direction. On the other side is what's known as the cathode department, and that is where reduction takes place, where the gaining of those electrons. So if you kind of super zoom into the picture here, essentially what's happening is the zinc in this case, which starts solid, zero oxidation state, loses electrons. And again, those electrons travel through the wire. And when it loses electrons, it goes from solid state to this aqueous ion, where it is starting to float around in the solution. And as these electrons go through the wire and down into this solution, those electrons will combine with the copper 2 ions that are floating there, and they will gain those electrons and become solid, basically. So you could kind of think about the solid is jumping from the solid into the solution on the anode side. On the other side, the ions that are floating around in the solution are gaining those electrons, sort of jumping out of solution and becoming solid on the other side. So you sort of have this transfer that occurs in terms of these electrons. Now, usually connecting these two sides is what is referred to as a salt bridge. And a salt bridge is pretty much what the name implies. It contains basically some type of salt solution, some type of ionic solution. And really the purpose of this is to keep the charge sort of balanced on each side. So you don't get such a buildup of charge that's occurring on one side versus the next. You can kind of see the chloride is heading this way, right? And the potassium is heading this way. So that makes sense based on what we're seeing happening here. If this cell continues to run, what's eventually going to happen is all these guys are jumping out into solution. So you're just going to generate a ton of positive charge, right? And over here on the other side, what's going to happen is all these positive guys are actually jumping out of solution. So what's going to happen is you're going to get this buildup actually of negative charge on this side. And since electrons are negatively charged, there needs to be sort of like a charge difference that occurs between one side versus the next. And you can kind of think of the cathode side as kind of being more positive, if you will, to kind of pull those electrons to the other side. But if you didn't have the salt bridge there, you could see you would actually build up more negative on this side, which definitely would not want the electrons to come across. It would probably stay over here because this side has the more positive buildup on this side. So the salt bridge keeps everything flowing. It also helps prevent sort of that buildup of charge that you really don't want, because eventually if you do build up that charge, this cell is not going to really work properly. That's not going to allow those electrons to go from one side to the next. So the salt bridge really functions that way. And again, that's why you see kind of the chloride coming down this way. Again, that negative charge is going to come in from the chloride in this example is going to kind of balance out a lot of that positive buildup we get over here. Same idea here as the potassium comes this way is going to put in some more positives over here, and again balance out that sort of negative buildup that you would get if you didn't have your salt bridge sort of attached. Salt bridge usually a lot of times a glass sort of tube, put some cotton or something at the bottom so obviously your solution doesn't fall completely out, allows for that kind of slow movement of those ions back into that solution. So since we do have sort of that potential difference between sort of the anode side and the cathode side, that's what keeps those electrons basically moving from one side to the next. And ultimately what's happening is we could use something like those electrons to do some type of work, you know, again, kind of similar to how a battery works. So those electrons go out, powers your device, sort of comes back. Now, if we look in this particular, we can see our two half reactions here. We have our zinc going from a zero oxidation state to a +2. So again, moving on that number line in this direction, becoming more positive, going through oxidation. And our copper here going from a +2 oxidation state to a 0, again, moving in the opposite direction, being reduced. And our overall reaction happening over here, our net ionic equation really, our net ionic equation, because in this case, the sulfate, it's really just spectator ions. They're just there to balance out the charge. And obviously that's why they don't appear here in our overall equation. So this is the general setup for really a sort of a galvanic cell you could build in the lab. On our experiment, I think we use filter paper, not so much beakers, but it works kind of the same way. But this is your traditional sort of setup. So anode oxidation, cathode reduction, electrons being pulled to the other side by a sort of difference in charge or potential, and it's going to drive those electrons sort of in this direction as well. So obviously you do need to know the galvanic cell and sort of this general setup. And as I mentioned, there is sort of this this difference in electrical potential between the anode and the cathode. And again, you can kind of think of it as sort of the pull on those electrons to help them come from one side to the next and keeping things flowing. And sometimes that potential was sometimes referred to as the cell voltage. A volt is basically 1 joule of work per coulomb of energy or charge is transferred. And that's what these units are, joules per coulomb. And you can see this is sort of the same galvanic cell, a little maybe hard to see, but there is actually a salt bridge right there connecting the two beakers, and just alligator clips on some electrodes in these solutions. And you can see here, just hooked up to a voltage meter, and you got a voltage of 1.1 volts. And as we will talk about, a positive voltage is usually a pretty good thing in terms of the reaction being spontaneous. Electromotive force is sometimes referred to as well, EMF, and also the cell potential. So sometimes in problems, you will be asked one of those three things, you know, calculate the cell voltage, calculate the EMF of the cell, calculate the cell potential. And really, they're all asking kind of the same thing. They're really just asking for the actual cell voltage in this particular case, as you can see here, 1.1 volts in that example cell that is in the picture. So another way that, in addition to sort of normal net ionic equations for redox reactions are written, and again, this would be a more of a net ionic equation. Maybe not as traditional as you may remember net ionic equations, where you write them for kind of double displacement reactions. They are often very commonly used for redox reactions, where it really just shows the two things involved in terms of what is being oxidized and what is being reduced. So again, as we did on the previous slide, oxidation state here being 0, this guy being +2, this being 0, and this guy being +2. So again, the zinc going from 0 to +2, going through oxidation, while the copper going from +2 to 0, going through reduction. Now, a cell diagram is this guy down here. And pretty much the way this is written is how a typical cell diagram is written for a reaction. So this reaction here and this cell diagram, they are obviously related to each other. And if you have the cell diagram, you should be able to write the equation like we see it on the page. And vice versa, if you have the equation, you should be able to write the cell diagram like we see there. So let's talk about sort of the parts of it here. The first part is we have what is usually the anode part of the cell. So that is where oxidation comes into play. So as we talked about, the zinc is what is going through oxidation, and it is technically the anode in the cell. And we have the zinc going to the zinc 2+. So truthfully, usually how these come about is we have our reactant, and then we have our product. So the reactant here is the zinc in the solid state. On the product side, it is zinc with the +2. So this is really aqueous ions, right? And we do sometimes give the molarity of this. Again, this would not have a molarity, as this is basically, I'll try to point to it, the solid electrode there, right? So this is the solution part of it, and it has a concentration of 1 molar. So we go reactant, 1 line, product in the anode reaction. And on the other side, we got our cathode reaction. which again, this is our reactant and this is our product. So if we look on the reactant side, that is our copper, which is aqueous and has a molarity of 1. And then our product would be our solid copper. So usually that's how it goes: reactant, product, reactant, product. The little 2 lines right here technically represent the salt bridge. And the salt bridge, again, is that connector piece that has that ionic compound in it that helps keep the charge from sort of building up. So anode to cathode is typically how these reactions are written in a cell diagram. And if you're given the cell diagram and you need the overall reaction, that's usually the way you could get it. So you look over here and go, okay, this zinc came first, so that's a reactant. This zinc came second, so that's a product. This copper came first, so that's a reactant. This copper came second. I'll go this way with it. So that's a product. So you can rebuild this reaction or equation from the cell diagram or go this way. So you do need to be able to obviously write a cell diagram. You need to be able to take a cell diagram and turn it into an equation. Any questions on how to do that? Now, essentially, there are a few other things that will occasionally kind of show up in a cell diagram. So here we do see molarity showed up. Sometimes, as we will see, sometimes an electrode may be a gas. So sometimes you may actually see some pressures involved. Again, because an electrode could be a gas, as we will see. So sometimes you'll actually see that as well. And usually when you see something like that where a gas is an electrode, because it's a gas, there's really kind of no physical solid version of it to really hook in as the electrode. So sometimes they may use something like platinum or carbon, or graphite is sometimes referred to. Write that better, graphite. And that is used as sort of the physical electrode that you would use for the cell when you have some type of gas. So occasionally in these cell diagrams, and we'll see a couple, I think, down the road here, you'll see some other stuff in there. And again, that's just sort of because of the nature of your electrode. So definitely when you have a gas, you oftentimes will have some type of pressure and usually some type of solid electrode that's not necessarily exactly the same as the gas or something like that. What we see here is 1 molar in terms of the concentration. So just to tie back to what we were talking about in the previous chapter, that you should recognize as also being sort of standard concentration, right? Standard conditions, 1 molar for concentrations. So that brings us to this idea of what is known as a standard reduction potential. And standard reduction potential is a thing that you hear a lot about in this chapter. It is sometimes abbreviated SRP for standard reduction potential. And in a standard reduction potential, as you could imagine, we will see a table of these reactions and of the values for SRP. So these are values like voltage type values. And we will see these guys here. But since there are standard reduction potentials, each of those reactions in that table will be written as a reduction reaction, which is an important thing to keep in mind. So for example, we take our zinc and we hook it up with a hydrogen electrode here. So this hydrogen electrode, as I mentioned, is a gas, right? Hydrogen's a gas. So this is a situation where you see the physical electrode is actually a platinum wire, for example. Again, because you can't have like a physical hydrogen sort of electrode. So we use this as a physical electrode for it. On our right-hand side, we have our anode. And we have our cathode over here. Again, electrons traveling to the cathode side. We also see that in our cell diagram. Again, reactant, product, reactant, product here. And you can see that in the overall reaction. Here's our reactant, and there's our product, and there's our reactant, and there's our product when you look at the cell diagram. Now, we do see similar things here. Again, the zinc is going from 0 to +2. So it is the oxidation half reaction or the anode reaction. The hydrogen here is going from +1 to 0. So again, heading to the left on that number line and going through reduction. R is the cathode sign. When we add these together, we get the overall reaction that shows just that, 0 to +2 and +1 to 0 in terms of the oxidation numbers. We also see what I was just talking about. Since hydrogen is a gas in the cell diagram, we don't talk about concentration, but we do talk about pressure, which happens to be 1 atmosphere as well, which again is standard pressure, right? And we see an additional thing added to the cell diagram, which is our platinum electrode. Again, because in this case, we're going to use that as our physical electrode here, it will find its way into a cell diagram. You will also notice, though, even though it finds its way into the cell diagram, since it just is really that physical sort of manifestation of that electrode, it does not find its way over here in the actual reaction. So it usually is included in the cell diagram, not usually included in the overall reaction as well. And usually in most cases, we don't usually include the sort of pressure and concentrations in the overall reaction either, but that's basically what's happening here. So any questions on that there? So how do we figure out really what all these sort of SRP values or standard reduction potential values are? And like anything in chemistry, we have to come up with sort of a standard to use. And that standard to use that they chose was actually that hydrogen electrode that we just saw. So that hydrogen electrode was used as basically the standard to compare everybody else to. And our standard reduction potential, which again, as I mentioned, SRP for abbreviation, is the voltage that's associated with a reduction reaction. So there is a table of these things. We'll see it shortly. And you may have to reference that table to solve some problems, but they are all written as reduction reactions. And this hydrogen electrode has a special name. It's sometimes referred to as She for the standard hydrogen electrode is basically what it's referred to. And if we look at our half reaction here, it is written as a reduction half reaction as our electrons are on the reactant side. So they assign this hydrogen electrode basically a value of 0 volts. So the standard hydrogen electrode has a SRP value of 0 or 0 volts. And this made it pretty easy because all they had to do now is essentially hook up the standard hydrogen electrode with other electrodes and measure the cell voltage. And then they could really figure out what the SRP values were for other elements going through this type of reaction. And that's essentially what we see here. So in this particular case, this is the one we were just looking at, really. This is our zinc. This is our zinc hooked up as our anode over here, where oxidation is occurring. And we have our standard hydrogen electrode hooked up as our cathode, in this case, as illustrated by this cell diagram that we saw. They basically hooked it up, and when they did, they saw that this cell hooked up exactly like this had an overall cell voltage of 0.76. So this brings us to an equation here, which you do need to know, and this equation will allow you to calculate the cell voltage for a galvanic cell, and you could take E of the cathode minus E of the anode. These are basically SRP values. So you can take the SRP value for your cathode minus the SRP value from your anode, usually found in a table, by the way. Again, the little knot that we see up on top, again, indicating sort of standard conditions like we talked about So 1 atmosphere, 1 molar, 25 degrees Celsius, very similar to what we talked about with thermodynamics in terms of those sort of standard conditions. So if we use this, we know that in this case, the hydrogen electrode is our cathode, which means the E of the cell was 0.76 volts. Our cathode was 0 volts minus the E of our anode, which in this case was our zinc. Rearrange this, the E of our zinc, as you can see on the bottom there, becomes 0.76 volts. And that would be the standard reduction potential for zinc. Again, you can see it here written as a reduction reaction. Again, gaining electrons, so zinc 2 plus is reduced to solid zinc minus 0.76 volts. So I'm just going to take a moment and talk about this formula here, and it's probably not going to make sense what I'm going to say now. But hopefully down the road here, a few slides, it will sort of make sense. So what we're going to see when we look at these SRP values, as we mentioned, is that technically speaking, they're all written as standard reduction potentials. Okay. When you look at a reaction like this, if we were to write our two sort of half reactions going on here, and I think we had 2 electrons plus 2 of these. This reaction here, which is our anode reaction, this is really an oxidation reaction, right? And this guy written like this is our reduction reaction, which means technically if we went to the table, what we would see is this reaction, and it would have a SRP value, an E value for it, right? Which is 0, by the way. Now, if we went to that table and we were looking for this equation, the way it's written, which is our oxidation reaction, we would not see it. We would see this equation. The difference between this equation here, for that you would find on the table, and the reality of what's happening in this reaction is the reaction is actually an oxidation reaction. So this is what is sometimes referred to as standard oxidation potential, is what this technically would be, not a standard reduction potential like what we got going on here. So technically speaking, when we reverse this reaction, as we will talk about, what happens to that E sign is technically it gets reversed. So when we technically use it like we are in this reaction and we flip it around, the E value that truly goes with the way this is written would then become positive 0.76 volts, as opposed to what we would find it in the table as negative 0.76 volts. So what does that mean with this equation? What it means with this equation is when we go to that table, and we'll see it shortly, we do not actually change the sign for the anode, even though technically, as you can see here, the way it's written, we should change the sign to positive. We actually leave it as negative, and that's why it is actually subtract here, because that will change the sign for you. So when we calculate E of the cell, it's going to be 0 minus a minus 0.76 volts. Those two minuses change the sign, and we get our positive 0.76 volts, which is again what they see in the cell. Now, you will sometimes not see this equation written like this. You will sometimes see this equation written E of the cell equals E of the cathode plus E of the anode. And the positive is nothing truly wrong with that version of the equation, except that it implies that you know that you're supposed to reverse the sign. And if you use this, you would actually change the sign and do 0 plus 0.76 volts, giving you 0.76 volts. So again, it may not make sense exactly right now, but we will see some more examples of this in just a second. But the rule is if you use this formula and you subtract, when you go to the table, even though really that reaction is reversed and really the sign has changed from what you would find it in the table, you should not change the sign because you'll get the wrong answer. If you want to do everything technically to the letter correct, and you want to make sure that you change the sign on the oxidation reaction, you should change the sign, but you should add the values. So the simple rule is if you subtract, don't change the sign. If you decide to add, you should change the sign and add those values together. You should not do both. Otherwise, again, you will get the wrong answer. So again, it may not make perfect sense right now, but we will see some more examples of that sort of situation, and I'll sort of point it out to you as we go through it. Any questions, though, so far? Okay. Now, here, if we hook up our standard hydrogen electrode with copper in this case, and we do our little sort of calculation, we see that the cell voltage is 0.34, and copper's SRP value will end up being 0.34 as well. We also see a change occurred here. In this case, the anode is the hydrogen electrode going through oxidation. The cathode here is actually our copper. So this also demonstrates a point that anything could be an anode or cathode. It may just work or not work depending on the cell voltage. So you could technically hook up anything as the anode or the cathode. Depending on the combination, may work okay, may not work okay. You could always switch them around if you needed to. By the way, if you hook two things up, you get a negative voltage. Basically, all you got to do is switch the two things around, and it will become a positive voltage. Make your anode your cathode your anode, and you'll be in business. So same thing here. We see that it also is switched in our cell diagram. Again, our anode over here, and our cathode over here. And our overall reaction now flips as well. This is our reactant and our product. As you can see, reactant and product. This is our reactant. This is our product. Again, reactant and product here as well. So in this case, we're doing the opposite. We're going from 0 now for the hydrogen to +1, becoming oxidized. And the copper is going from +2 to 0, gaining electrons and becoming reduced. So they basically hooked up the standard hydrogen electrode to all kinds of different guys and came up with these SRP values. Here's a table. I don't think this one's actually from your book per se, but like you have a just as nice as a one, I suppose, that lists all the SRP values, which clearly you can see and memorize. I'm just kidding, don't memorize. But one thing that if you look at all these as you come through here, these are all something plus some electrons. Again, these are all SRP values, which is these E of the cells here, our E values over here. Now, these are all, again, reduction reactions that are written. So as we've been talking about, since a redox reaction is both an oxidation and reduction reactions, it technically means, as we were just talking about, that when you take a reaction off of a table like this, one of those reactions that you take off, you technically need to reverse and make it an oxidation reaction versus a reduction reaction. Now, again, that's where you get your choice as to how you want to do the calculation. Technically speaking, when you reverse it, the sign that you find on the table should also reverse for how it's written. And if you do that, again, you should add those numbers together and not subtract. If you want to subtract, you could just take the value straight from the table and subtract it to the minus will change the sign for you. Here's another table, which clearly you could see with a magnifying glass, I suppose. But let's just talk about some things that we do see in a table like this. The E is written for the reaction, for how it is actually written. So technically speaking, as we've been talking about, if you're talking about the zinc plus the 2 electrons going to our zinc, the E value would be that one that you found on the table. But technically speaking, if you reversed it, which is what this says right here. If I reverse that reaction around like I was just talking about, the E value here would then become positive 0.76 volts. So if you're asked to write the half reaction for the oxidation part or the anode part, you should write that equation I just wrote. And if you're asked what is the SRP value or E value for it, you should write positive 0.76. If you're asked to write the reduction or the cathode reaction, top one there, and the E value like you find on the table. Now, a question may come, how do I know who's the anode, who's the cathode, right? When you put these two things together. And it's a good question. You could just flip a coin and hope for the best. It might come out okay. But there actually is a way you can use the E values. So the E value that is more positive typically will be the guy that will be reduced. So when you're putting two things together and you go to the SRP value, the value that you find that is more positive will typically be the one that's reduced. So what does that mean in terms of the galvanic cell? If you remember, it is the cathode, right? That is where reduction occurs, which means the more positive E value from the table is typically your cathode and how you should hook it up. So that's how you can figure out if you're just given a problem where they say, hey, you put this together, these two guys together, and made a galvanic cell. You could go, okay, I went to the table, the SRP table in the book. This guy has the more positive value for the SRP value. That means that he should be the cathode. And by default, the other one should be the anode. Now, there is a very big asterisk that you put next to this little kind of thing. And the big asterisk is this. You only use that when you are not given any other information. And what I mean by that is you're not given a overall reaction that's happening. You're not told in words like this is reacting with this. You're not given any of that information. You're just simply told, hey, you took this guy and this guy and you built a galvanic cell. Congratulations. You know, what is the anode or cathode? That is the situation when you would use the more positive. If you are given an overall reaction, you actually have to look at the reaction to see what's happening. So in the overall reaction, if you're given it, you should look and see what is being oxidized, and that would be your anode, and what is being reduced, that will be your cathode. And if you are given an overall reaction, that may disagree with the more positive number value. So only use the more positive E as the cathode when you're not given any other information. Again, obviously, if you're given other information, you should use it. Probably is why they give it to you. So continuing on here, as we sort of touched upon there, the half reactions are reversible. So every single reaction that you see in this table, which are all written as reduction reactions and cathode reactions, you basically can flip them and write the oxidation reaction. Now, when you do flip it, as the next thing says, when we do flip it, technically speaking, the E value that you find in the table should also be reversed, because your products become your reactants, reactants become products, the overall sign basically changes. Something that is very different from, say, thermodynamics is the idea that if you remember, like in thermodynamics, and it does happen here with sort of redox reactions as well, you oftentimes will need more than what is given to you. And what I mean by that is, say you had a delta H value and for that reaction, and you needed 2 of everybody. So you multiplied everybody by 2. You would then take the delta H value and multiply it by 2. In redox reactions, as we've seen, occasionally you will need to multiply each reaction by a common number. And the purpose of that in sort of redox reactions is to make sure that we have the same number of electrons. The difference, though, is if you multiply a half reaction by a common number, you actually do not multiply the SRP value by that common number. So if you needed to multiply by 40 to get the right number of electrons, the SRP value for that reaction will not be affected by that. So you do not do that. So that's a major sort of difference in sort of thermodynamics as we talked about. Any questions on that so far? All right. So let's take a look here, I think. See what you did here, see what you got going on. All right. So why don't you try this? Why don't you calculate the standard EMF of the cell, or the cell voltage, for an electrode made up of cadmium and chromium. Let me spit that out. And these are the SRP values that you find from the table. Why don't we add a couple of things for here? Why don't you write the balanced overall net ionic equation that's happening? Why don't you figure out the anode and the cathode? And while you're at it, why don't you write the cell diagram for it as well, just to make sure. So add a few of those things, write the overall reaction, which I wasn't looking for. Net ionic equation. Why don't you do a little cell diagram just to make sure? Obviously identify the anode and the cathode, and also do what it asked, which was E of the cell. All right, so why don't you take a minute or two and see what you come up with on that. Okay, so let's take a look here, see how we're doing. So let's first start off with, we have a galvanic cell basically, and we're basically just told pretty much that we're putting together it with cadmium and chromium. So we want to determine which one is our anode and our cathode. So we can use the SRP values, which is where these come from, that table that we just saw. And here we do see that the cadmium is more positive. This guy is more positive, even though they're both negative, which would imply that the cadmium here should be our cathode. And by default, the chromium here should be our anode. So again, in this case, we weren't given any information about what is happening in this reaction. So we can use the SRP value that we find in the table. Now, if we want to write the balanced equation, because this is technically our anode, and anode is oxidation, this reaction is not written as an oxidation. This reaction is written obviously as a reduction reaction. So if we want it correctly, we technically would have to reverse this reaction. And what does that do to our SRP value? Because we reverse it, it now becomes positive 0.74 volts. Okay. Now, in addition, I'm just going to kind of gently put not very gently. We'll go put a line through there. We're going to add our cadmium now and our chromium together because we want the overall reaction. We also need to multiply this top guy by 3 to get the right number of electrons. We need to multiply the bottom guy by 2 to get the right number of electrons in this one. The number of electrons we're shooting for is 6, right? So that they will cancel out. And if I do that, I'm just going to rewrite everything up on top. So 3 cadmium plus 6 electrons gives me 3 CD solids. Now, my E of the cell in this case does not change. So that's what we were just talking about on that table. Even though I had to multiply this guy by a common number, it will have no effect on E of the cell. So it remains the same for that half reaction, or the SRP value, I guess is a better way of saying that. We also are going to multiply our bottom one that we did flip, which would be 2Cr solid, goes to 2Cr3 plus and 6 electrons. Now the E value on this one also not going to be affected by the multiplying by 3 in this case, or 2 in this case. And it is, though, going to be affected by what we did earlier, which is flip it. So this is going to be positive 0.74 volts. This means that when we add these two half reactions together, which is what I asked for, the electrons should cancel like a normal redox reaction. Everything on the left stays on the left. So we have 3CD2 plus 2CRS goes to 3 cadmium plus 2 of the chromium with a plus 3 charge. So this guy right here would represent our balanced net ionic equation for what's happening here. 3 cadmiums on both sides, 2 chromiums on both sides. Overall charge on the left plus 6, overall charge on the right plus 6. This would technically be the balanced net ionic equation. Any questions on that so far? So let me just clear out some room, maybe up here. So we have somewhere to write. Okay. So we were also asked to hang on here, get my eraser to go away. All right. We were also asked here to figure out E of the cell, which is really what the question is. So now I'm going to demonstrate the two differences that I was talking about a second ago. If you were just asked, like you were in this particular problem, truly, to calculate E of the cell, you could do the E of the cell is equal to E of the cathode minus E of the anode. And again, if you were to do that, you are going to subtract, which means I would use the two original values that I would find from the table, and I would take E of the cell is equal to my cathode, which is minus 0.4 volts, minus the minus here that was there, that I would find from the table, 0.74 volts. Again, that negative is there to change the sign for me, and I will get 0.4 minus 0.74, and we'll get 0.34 volts. Which is positive 0.34 volts as our cell voltage. So that is one way that you can calculate the cell voltage here, by simply just going to the table, identifying what's your cathode and what's your anode, and putting the numbers in exactly the way that you find them. Now, there's some people that want to do everything, like I said, technically correct. And technically correct, this value is not correct for what's happening here. This value is correct for what's happening here. And if you decided to change the sign like we did here, we can just add those together. E of the cell would be minus 0.4 volts plus 0.74 volts, because we changed the sign, and we would get 0.34 volts. I think I just got your question, I think. Yeah. Okay. So it is really your personal preference. Okay. So I would say you should choose one way and kind of stick with it. If you want to change the sign, which technically is the right value for the way this guy is written, you should change the sign and then add the numbers together. If you just want to quickly figure it out without worrying who's flipping the signs or all that, that is truly why it is subtract here, because it will basically change the sign for you. So they both, as you can see, will get you to the exact same answer. It is really just your personal preference which way you want to do it. And like I said, I probably would choose one way and kind of stick with it. What you don't want to do is change the sign and then add it together, because then you're going to get the wrong answer. So you don't want to change the sign. I'm sorry, change the sign and subtract, because it will undo it. So to answer your question, that's what I just said. You don't want to change the sign and then subtract, because you're going to undo it. So if you change the sign, you need to add. If you don't change the sign, you should subtract, because that's really what the minus is for, because it will change the sign for you. Because it's always going to be the anode one that's going to change, and that's why the minus is there. Okay, let me just read your questions. Hang on here. I think I just answered yours, I hope, about the sign. So again, don't change the sign and subtract. If you want to subtract, don't change it. Keep the sign like you find in the table. To answer your question about how you know which one is the cathode versus the anode, when you have no information given to you, other than like in this problem, they're like, hey, you just made a cell out of these two things. You could use the SRP values that you would find in the table, and the one that is more positive would be your cathode. Now, if they do give you an overall reaction, which we'll see some in just a second, you do have to look at the reaction to see what's happening, who's being oxidized and reduced. And whoever's being reduced obviously would be your cathode. Whoever's being oxidized would be your anode. But again, if they don't give you any information, like in this problem, they didn't really say, hey, the chromium is our anode or the chromium is our cathode, or they didn't give us the overall reaction, we could use the SRP values to determine. Again, more positive would be your cathode. I think I got everybody's questions, I hope. Yes. So, yeah, for the most part, you're correct in your questions. The questions are, would they ever ask you sort of the values of the cathode and anode? There are questions that may ask you that, but it's probably going to be more in the context of calculating E of the cell. So overall, it would be probably more in that context of E of the cell. But I have seen textbook problems sometimes where they ask you just to write the the anode half reaction or the cathode half reaction, and sometimes they will ask you for sort of the E value associated with that. So in that sort of specific type of question, it's possible, but you are probably correct. In most cases, it'll be used to sort of calculate E of the cell and stuff like that. So I would say a very small probably case, you would be asked specifically for that. But again, in that sort of conjunction of calculating the E of the cell. Other questions on that? Okay, so I think I got everything. I think the only thing I didn't put up there perhaps was the cell diagram, right? So we would have our anode and our cathode. So again, our anode, as I wrote around, is our chromium here. So our chromium was our anode. So if we do sort of a cell diagram, I'll try to squeeze it right here maybe. So we would have our chromium, right? Going to our chromium 3+. Also, you want to get really technical, put the molarity there. Then we would have our cathode side, which would be our cadmium, going to our cadmium, the solid over here. So sorry, I kind of squeezed it in there, but it'll look something like this. You could put the coefficients in if you wanted to, but sometimes people will leave them out and just they figure you'll balance it out when it's all said and done. Any questions on any of that there? All right, why don't you try maybe another one here and see what you come up with. Galvanic cell is made up of magnesium and silver. Why don't you calculate the cell voltage for this one and see what you come up with. Okay, so let's see what we got going on here. So again, here we're not really given any information about how this reaction is occurring. So we can find these values again in that SRP table. And we want to be looking for, in this case, since we're not given any information, what one is more positive. So this one being more positive should be our cathode, right? More positive. This one being obviously not as positive would be our anode. So although it didn't, again, technically ask you to write a balanced equation or anything like that, technically speaking here, if we were to reverse it, this is the one that technically should be reversed, which means that we would technically have the silver with its E value there from the table of 0.8 volts. We technically would reverse the bottom one, which means we would have the magnesium going to magnesium +2 plus a couple of electrons. And now, again, technically, since we reversed it, to write the correct value, it would be positive 2.37 volts. And we would also need to multiply the silver half reaction by 2 to get the right number of electrons. Remember that that will not have an effect on the SRP value. And that means that our electrons would cancel. And the overall reaction here would be our silver plus our magnesium going to our 2 silvers and our magnesium with a +2 charge. And if we were going to calculate our E of the cell, we could do it again one of two ways. If you did your cathode minus your anode, again, I'm going to subtract here, which means I'm going to use my original values, which means I will end up with 0.8 volts minus a minus 2.37 volts, which will give me 3.17 volts, which is a positive voltage and a good thing for the cell in terms of spontaneity. Again, here though, if you're sort of a purist, if you will, and doing everything to the letter correct, you would then want to add these instead of subtract, because you already changed the sign. And you can see here, you will get, I'll put in parentheses, the same number. So again, like I said, I personally don't have a preference which way you do it. But like I said, I would probably choose one and kind of stick with it. I will say, just to sort of run home that point, if you were asked, kind of like the earlier question, if you were asked to write the anode reaction with the correct E value, again, it should technically be this guy here with the positive value and obviously the reaction reverse. So if you did get a specific equation or a specific question where it asks you to write either the anode reaction or the cathode reaction, remember, like that table said, the E values are specifically for how it's written, which means if you specifically wrote this equation and you did not flip that E value in terms of the sign, technically speaking, this is incorrect, because that is not the value that goes with this reaction written in that direction. The value that should go with it is the positive 2.37. So again, just in case you do come across sort of a specific question like that, you want to make sure that you do adjust the E value correctly for how it's written. Any questions on that there? Okay, we are going to stop here today, and also a couple of things before we go to lab. Lab today is experiment 15, I think. So that's some thermodynamics and all that kind of stuff. The exam is scheduled for 1 week from today, but actually there has been a change in terms of the lab schedule and everything. So the exam will be 1 day later. That's never a bad thing, I suppose. So the exam, I think, was originally scheduled on the 21st, was originally the exam. The exam will be on the 22nd. The experiment, which was on that day, which I think is group 4, I want to say, will be moved to the 21st. So we're going to swap these two places. So the next exam will be on the 22nd. And the experiment will be on the 21st, just so you know. That's what's coming up next week. Any questions on that there? Okay. Other than that, we will start lab in about, I don't know, we went a little bit long here. So we'll start about 5 after 3, and we're going to do experiment 15. Make sure you type here if you haven't done so, and I'll see everybody in about 10 minutes or so.